Good day, everybody. Thank you for joining in. So this is a Electromagnetics 344 lecture, which is on the use of this awesome graphical tool called the Smith's chart. It's also covered in your textbook in section 9.6. So you can read that section for more thorough detail about exactly what this graphical tool is, but I will explain to you also now in this lecture the most important components. Okay, so this tool is linked to our transmission line calculations, which at this point you should know consists of some sinusoidally varying source with a source impedance, and at the source terminals we have connected this transmission line, which is characterized by the characteristic impedance and also the phase velocity. So remember, phase velocity here indicates that the voltages and the currents on this transmission line is represented by traveling waves, a forward propagating wave and a reflection. And then at the load terminals, at the end of this transmission line, it is terminated in what we call a load impedance. So this impedance can be complex, consist of a real part and an imaginary component. And depending on this load impedance's value, if it is anything other than the characteristic impedance. Okay, so as I was saying, we have a load impedance here connected to the transmission line that consists of, that has a characteristic impedance. And what happens is when this load impedance is anything other than this characteristic impedance, we will have a reflection over here. So this effect we quantify using this voltage reflection coefficient, which is essentially the ratio of the reflection to the incident traveling waves. And as we showed in previous lectures, this can also be written as just in terms of the load impedance and the characteristic impedance, as shown over here. And this value is typically complex, which is denoted like this, with a magnitude and some phase. The reason that it's complex is because this load impedance is in most cases complex. All right, so solving these equations, we will look at this one at a later stage. Solving these equations is in some cases quite challenging because it involves quite a bit of complex impedance calculations, especially in the early in like 1940 when this work was focused on, when the people didn't have nice calculators and computers to do these complex calculations on. So this engineer called P.H. Smith invented a graphical way in which to easily do these calculations. So as I said, the Smith chart is a graphical way in which to do these calculations easier. It is a graphical plot of what we will see the normalized resistance and reactance functions. So we'll look at that in detail now in this lecture. And we plot this on the reflection coefficient plane. So what we will look at is the derivation for a lossless transmission line. And this is covered in your textbook, section 9.6 on these pages over here. And we will focus on this calculation here, which essentially links the reflection coefficient, which is complex, to the load impedance and the characteristic impedance. Okay, so let's do that. Okay, so these are additional notes that I just essentially show you where this Smith chart comes from. And as I said, we're starting off with this equation over here, which links the input reflection coefficient to the load impedance and the characteristic impedance. Okay, so let's take that equation. It is considered over here, and the transmission line that we're looking at is lossless. So our characteristic impedance is just some real value denoted here as R0. Okay, so this expression over here, we can also rewrite it by taking the denominator over here to the left hand side. So we have, which is shown over here, and then I can rewrite this equation as shown like this in equation 2 over here. So I have on the left hand side my ZL, the load impedance. I divided by the characteristic impedance of the line, or the resistance in this case because it's lossless. So what I have then is a normalized load impedance, which I denote here ZI prime. Sorry, ZL prime. And the book, this is just denoted by a small letter, but it's difficult to distinguish between capital and small letters on the note. So I put a prime over there. And this is equal to 1 plus gamma divided by 1 minus gamma. So we're working with this equation, which is just a different format of this one. All right, so firstly, the quantity here on the left-hand side, ZL normalized by the characteristic resistance of the line, is a complex number. It is denoted by R plus JX. So R is the resistive component, the normalized resistive part of the load, and X is the reactance. So obviously, positive X is inductive reactance, negative X is a capacitive reactance. But this is the normalized load impedance. Okay, and also gamma, as we said in numerous cases, gamma is a complex number, so it consists of a magnitude and a phase. This is gamma represented in what we call the exponential form of a complex number, but we can also represent it as the rectangular form of a complex number. So we have gamma R plus J gamma, there's a little I short there, but gamma I. Okay, so then if I use this representation for my reflection coefficient and this representation for my load, then my equation 2 can be written like this. R plus Jx, which is my normalized load impedance, is equal to 1 plus gamma, which is the real part, plus J, the imaginary part of gamma, divided by 1 minus the real part of gamma plus J, the imaginary part of gamma. Now this is a complex number divided by a complex number. How did we learn in first year to resolve this? Well, we multiply both the numerator and the denominator by the complex conjugate of the denominator. Okay, so complex conjugate is just the real part of the denominator and the opposite of the imaginary component. So this is the plus J gamma I. So I multiply this out, and then I get a longish equation or a longish fraction that looks like this. Okay, and this can be separated into both a real part and also an imaginary part. Remember, so if I simplify this and I set the real part equal to the real part over here, I get this equation over that I see here. And if I can also, likewise, I can also equate the imaginary component over here with the imaginary component of the normalized load impedance, which is written here. So equation 3 and equation 4, this very clever P.H. Smith in 1944 looked at, and then he identified something very cool. So let's take, for example, equation number 3. See what did he identify. So he saw that equation, if I can just slip back here, this equation can also be written for fixed value of R in this form, where I have gamma R minus R over 1 plus R plus gamma I squared is equal to 1 over 1 plus R squared. Now this form you guys should also be able to recognize. Well, it looks very much like the equation for a circle, that's just translated along some point on the x-axis. So look at it. I have x minus x0 squared plus y squared is equal to r squared. So we see that this equation represents circles with a radius of 1 over 1 plus r, and it's centered at gamma r, so the real value of the reflection coefficient is centered at r over 1 plus r, and the imaginary component value of gamma I is equal to 0. That's where this circle is centered on the complex reflection coefficient plane. Okay, so let's start off with the complex reflection coefficient plane. Well, it consists here of the imaginary axis. Sorry, it slips. It consists here. Okay, I hope we're back now. Consists here of the imaginary axis, gamma I, and a real axis, gamma R. And then I know that obviously the magnitude of gamma, which represents this unit circle over here, has to be less than or equal to 1. That's the limitation of my reflection coefficient. And then its phase is measured just from this real axis. Okay, so let's take a particular value of R in this equation over here. Let's take, for example, R is equal to 0, which represents, if we only consider a resistive load, a short circuit. What would happen? So if RL is equal to 0, we find set 0 in here, set 0 in here, that I get an equation that looks like this. Gamma R squared plus gamma I squared is equal to 1. So for R is equal to 0, the reflection coefficient traces out this locus over there. So this is what we call the R circle. So anywhere along this R circle, R is equal to 0, I get a reflection coefficient magnitude of 1. Let's take another value. Let's take, for example, this red one over here, which is valid for R is equal to 1. Small r is equal to 1. So if I substitute into, let me just zoom out a bit. If I substitute into this equation over there, R is equal to 1, then I can simplify my expression for my circle to look like this. Gamma R minus a half, 1 over 1 plus 1 is a half, so squared plus gamma I squared remains there, plus the radius of a half. And this I can plot on my complex reflection coefficient plane, which is just a circle that's centered at a half over there on the real reflection coefficient axis. 0 on the imaginary reflection coefficient axis is equal to a radius of half. So I put the center over there, trace out a half like this, and I get then for this red circle, which we call the R is equal to 1 circle. So for normalized load impedance values of 1, this is the values that the reflection coefficient can take on. What if R is equal to infinity, so essentially an open circuit load impedance? Then my reflection coefficient, this expression for the circles looks like this. So I have essentially infinity over infinity. Well, this just becomes 1, right? The limit of R tends to infinity of R over 1 minus R is equal to 1. Gamma I squared just remains gamma I squared, and the right hand side, the radius 1 over 1 plus R. For very large values of R, this will tend to 0. So essentially I have a circle that is centered at the gamma R is equal to 1, so this point, and gamma I is equal to 0, so exactly that point over there with a radius of 0. So it becomes this blue dot. So we see that on this Smith chart, on the complex gamma plane, an open circuit that is a very large normalized load impedance will be located near this side. Okay, so some observations. The center of all the R circles, that is for fixed normalized load resistances, lies on the gamma is equal to the gamma R axis over here. These R circles becomes smaller as the normalized load resistance becomes bigger, and all circles will pass through this point over here. Gamma R is equal to 1, and gamma I is equal to 0. Okay, so this is now what happens for fixed values of R and gamma. And we got this behavior by looking at this equation over there. Now we are going to look at the X, so the reactance circles, which is essentially derived from this equation over here, this number 4. So let's see what this looks like. Okay, so we are considering this expression over here, and Smith showed that we can rewrite this in this form, which also looks like circles. That is situated at the gamma R, the real part of the reflection coefficient, equals to 1. So along this line here. And the imaginary part of the reflection coefficient is just equal to 1 over x, where x is the normalized load reactance. And the radius of these circles is equal to 1 over x as well. So let's, again, similar to R, take a few of our our reactance values. So let's take, for example, a reactance of 1, which is inductive. So if I substitute 1 into this expression, x equals to 1 in this expression over here, it becomes shown like this. So I have a circle that has a radius of 1 that is situated at gamma R equal to 1 and gamma I equals to 1. That is on the complex reflection coefficient axis. The circle starts over there and it has a radius of 1. So this distance over here is equal to 1. And I trace out this circle. Now, the only valid component is this blue line over here, where the reflection coefficient magnitude is less than or equal to 1. I think you guys can remember why that is. That is because the reflection coefficient is a ratio between the reflected voltage wave and the incident voltage wave, or the magnitude of the reflection and the incident one. And that has to be less than or equal to 1 for lossless lines. Okay, so what happens? Let's take another value. X is equal to -1. So I substitute this into my expression over here, and I get something that looks like this. So gamma R -1. So my center of that circle is going to lie somewhere on this axis. Gamma I is equal to -1. So I'm going to trace out the x is equal to minus circle by putting my origin here. And the circle has a radius of 1. And again, the only valid points is where the reflection coefficient magnitude is less than or equal to 1. So anywhere along this line, the normalized load reactance will have a value of 1. And anywhere along this line, the normalized load reactance will have a value of -1. So this part, negative reactance, is capacitive, and this part on the Smith chart is inductive because it's associated with a positive reactance. What happens when we have a short circuit? So X is essentially 0. The normalized load reactance is 0. Well, then we find 1 over X tends to infinity. And what happens then with our expression over here? So the center of my circle will still remain on the gamma R is equal to 1 plane or line, which is somewhere along here, but the imaginary component will sit at 1 over 0 at infinity, right? So it sits way on top here, and it also has a radius of infinity. So a circle sitting right on top there with a very big radius essentially traces out this axis. The gamma R is equal the gamma R axis over here, this purple line. So anywhere along that line is a short circuit, is where our normalized load reactance is equal to 0. Okay, so some observations, as I mentioned already. For positive normalized load reactances, we have an inductive circle, and these circles lies on the top, on the positive part of the Smith chart. These reactive circles that lies at the negative part of the reflection coefficient plane is our capacitive loads, represents our capacitive normalized load reactances. The X circles become smaller as the reactance values becomes bigger. That we also saw for the resistive part, and they all and again they go through this point over here. So this point is, let's see what this point represents. So let's take again a very big load reactance, so X is equal to infinity. What happens to our expression over there? So this part remains as is. Let's say the x-intercept, or the real part of gamma intercept, it's also on this line. This part, gamma I minus 1 over infinity, essentially just becomes 0. So that is the point where my circle begins for a very big normalized load reactance. And the radius over there, 1 over infinity, essentially becomes 0. So again, I see that for very large normalized load reactances, I get a point on the Smith chart that sits over there. So all the points on the Smith chart on this side represent an open circuited load, and on this side we have the short circuit load situation. Okay, so all together now, how is all this information going to help us? So what is shown on the Smith chart is a combination of R and X circles on the complex reflection coefficient plane. So this is the imaginary part of gamma, the real part of gamma. And I look at these X circles, which is shown over there, right? And there's obviously many more of them. I only show a few here for conciseness. And I also have these R circles, which has their origins on the gamma is equal to R axis. So let's take only a few now. I have this blue line, which is represented by a normalized load reactance of 1. And I have this red line, which is a normalized load resistance of 1 also. Now, it can be shown that these circles, these R and X circles, are orthogonal to each other. So if I find the point where they intersect, I can actually read off the value of my load impedance. And in this case, let's take this point, the R is equal to 1, X is equal to 1. So I can see this point, obviously R is equal to 1 and X is equal to 1 represents a normalized load of 1 plus J, but it's normalized. So to get the true load impedance, I need to multiply it back again by characteristic resistance over there. So my load impedance has a value R plus J R0. Now, what this graphical tool allows us to do is to, at this point, read off the value of gamma, which is the magnitude over there. So by eyeballing it, it's obviously less than a half and a bit more than, it's a bit more than longer than a half, and obviously less than 1. This magnitude over there is 1 right at the edge. So if I'm only looking at that part, well, then it's about, let's guess about 0.7. And then it has an angle over here, which more or less looks around about 45 degrees. So I have a reflection coefficient of about 0.7 angle 45 for that particular load impedance at point A. Now, the cool thing about the Smith charts is that you can also check your calculations. And how do I do that? Well, I know what my expression is for my reflection coefficient calculation. Gamma is equal to ZL minus R0 over ZL plus R0. So let's substitute for ZL now this value in here, R0 plus J R0. Well, then this simplifies to 1 over square root 2 angle 45 degrees, which is more or less what we estimated from our graphical tool over here. Okay, so this is the first thing that I think you should know of Smith charts, is that we have these R circles, we have these X circles, the points where they intercept. I can read off a particular value for gamma. And the other way around, I can plot a particular value for the reflection coefficient, and then I can find the particular load impedance that is that will result in that value for the reflection coefficient. And other cool features we will be looking at in our next lecture. Thanks, guys.